Good evening, students, and welcome to the live Aha Guru session for Standard 12. Okay, we are going to continue with matrices that we started last class. Okay, so let me go ahead with that. But I hope by now everybody has finished the online lesson. Okay, because last class we saw that quite a few had still not completed it. The same lesson has been assigned. Okay, just to make sure that everybody is thorough with uh, whatever is the, the background and the theory that we did. Okay, so the worksheet also has, we started with the worksheet which we have not completed. One more new worksheet will also be shared with you. Okay, just give me a moment. Okay, so as usual we will do a very quick recap. Okay, so basics of matrix. What is a matrix? Okay, square matrix, diagonal matrix, etc. We saw. Next, operations. Okay, and commutativity, associativity on addition is something that we saw. These are all basic stuff. Then the most important new operation is multiplication of matrices. Okay, matrix multiplication is defined as capital C is equal to Cij m cross P, where C is equal to AB is given by this. Okay, um, and matrix multiplication has this beautiful property that associativity is true even though multiplication is defined in a complicated way. Okay, then but commutativity is generally not true. And for square matrices you can define things like a square, a cube, etc. And then we looked at transpose of a matrix. Okay, transpose of a matrix is defined by, it's defined as the matrix that you obtain by interchanging the rows and columns. Okay, so A transpose is a matrix B, which is given by Bij n cross m. Bij is Aji. Okay, and transpose has some properties. A plus B whole transpose is A transpose plus B transpose, A minus B whole transpose. Because matrix addition has the simple property that you, for A plus B you can just do Aij plus Bij. Similar things you can do. AB the whole transpose is defined as B transpose A transpose. The inverse part we'll come to later. Okay, then we also saw that a matrix is symmetric, skew symmetric, etc. We also defined that. Okay. Um, okay. Then one or two ideas in the theory we haven't gone through in detail. I'll do it today. Okay. About orthogonal and all that. Okay. So for the next big idea is inverse. Okay. Inverse is what we had started with. A square matrix A is singular if determinant A is 0. If determinant A is not 0, A has an inverse given by capital B is equal to A inverse. This is what we had done. AB is equal to BA is an important property in inverse. In general, AB and BA are not equal. In general, for two matrices A and B, but if B is equal to A inverse, and AB is equal to BA is equal to IN, where A is n by n, B is also n by n. Remember, inverse is defined only for square matrix, and the most important idea about inverse that we learned last class is inverse, if it exists, is unique. Okay? And then some properties like A inverse, the whole inverse is A. Okay, Now, inverse is most useful when you want to solve an equation like AX is equal to B. In fact, if somebody asks, "Sir, why are we even learning matrices?" It's just some putting all the numbers that we know in some row column form. What is the big deal about it? What is so special, useful about something like this? I mentioned it last class itself. Matrices are useful only in the context of solving some other problem. And the main problem that matrices will help solve is a system of linear equations, which is also something that we'll try and see today if possible. Okay. Now, there is no division of matrices in matrices. In equations, you can divide both sides by A. So, equivalent of division is inverse. So, you say A inverse times AX is A inverse times B. Since AX and B and a very important idea that in matrices, note this, in matrices B equals C implies AB equals AC, but AB equals AC does not imply B equals C. Also, B equals C implies BD is equal to CD. This is called post multiplying by D, and this is called pre multiplying by C, sorry, by A. In an equation, you can pre multiply or post multiply both sides of the equation with the same matrix. That is like saying if I have x is equal to 3, I can write 3x is equal to 9. Obvious, because you can multiply both sides by 3. But you can also write x into 3 is equal to 3 into 3, which is the same. Because in numbers, commutativity holds. So we don't bother saying 3 into x equals 9 is different from x into 3 is equal to 9. Because 3 into x and x into 3 are the same. But in matrices, because commutativity is not true, you you can define pre-multiplication and post-multiplication as two separate operations, and both are valid. Okay, I hope this is clear. Okay, and then some other okay, now one of the most important properties is AB the whole inverse. I think we derived this last class. We proved it. AB the whole inverse is B inverse A inverse. We proved why AB the whole inverse must equal B inverse A inverse. How did we prove? Because inverse is unique. If you actually multiply, just give me 1 second. Okay, if you multiply AB with B inverse A inverse, you get I. That is why it is proved that AB the whole inverse is B inverse A inverse. If you multiply two matrices and you get I, one is the inverse of the other. That is the uniqueness of inverse. The uniqueness of inverse is a very useful idea. Instead of instead of struggling hard to find an inverse, you can just guess an inverse just by seeing what if I multiply with, I'll get I. And that actually gives you the inverse as a a proper this thing, not like a guess. Okay. Then for 2 by 2 matrices, we saw what the inverse would be. Okay. Actually, there's a small. Okay, these matrices should have been square brackets. I think by mistake it was put as round bracket. Matrices should generally have only square brackets. This is all that we did, and then we are also done question 10. Okay, I think this is where we left last class. Okay. Um, okay. So let's start. If you have any doubts in whatever has been covered, maybe at the end of the class there was no time. Okay. Okay. I'm going to answer doubts only on what has been covered so far. If you're going to ask me something else, sir, what about this topic? What about that in the online lesson, etc.? You have to wait. Okay, for the later half of the class. Okay, I will also enable the chat. Like I think we did that last time. I don't remember when we enabled, but so I will enable YouTube chat so that you can post some of the things there also. Okay. Okay. While we wait for the doubts, I think we can move on to question 11, the number of matrices which have an inverse. Okay, so please go ahead and do question 11, where capital A is a 2 by 2 matrix. Remember, A inverse is 1 by, okay, this is what we have defined, 1 by AD minus BC, B minus B minus C A. So you can check that A B C D into D minus B minus C A is actually AD minus BC 0 0 AD minus BC. This also I think we did. Okay, Siddharth. Um, Siddhartha Rishikesha has made an excellent observation. I gave this as a challenge question. Okay, that to write 2 by 2 matrix as A squared is equal to XA plus KI. Actually, what you are saying is A squared, not minus, or minus XA plus K, XA plus KI. Okay, yes, you're right, Siddhartha. I don't remember the exact value of, but you're always able to write, so you'll be able to solve for X and K. Okay. Please go ahead and solve question 11. How to find the inverse? I haven't taught Pramula Pravika. Okay. Okay. I've told you how to find inverse. Inverse for 2 by 2 matrix. How to find inverse for 3 by 3 or 4 by 4, I haven't taught you. But what I've told you is if an inverse exists, it is unique. If you are able to guess an inverse, then it's unique. I haven't come to how to find an inverse. I'm going to do that. It is there as part of today's class. It's there in the online lesson as finding inverse using elementary operations. I am going to do that. Okay. Okay, you will learn how to find inverse. Is there inverse for I? Very good. Yes, there is, because I into I is equal to I. We know that. Therefore, I inverse is equal to I. I is its own inverse. Okay. Good question. Okay. Kirtana has asked, Kirtana Sriram, C inverse exists. Can we say AC is equal to BC because we can post multiply C inverse on both sides? No, actually, your question, I think you mean that if C inverse exists, then AC is equal to BC implies A equals B because we can post multiply by C inverse on both sides. I think this is what you meant, and that statement is correct, and it is also very crucial and important. That's why I'm writing it explicitly, and it's a very, very important statement. Kirtan, I think you just made a mistake by forgetting to put the implies. This is a very important idea that if C inverse exists, it's almost like you can cancel C, but the way to do it is actually multiply by C inverse. There is no cancellation. There is no division by C. Multiplying by C inverse may give the same result as division by C, but that doesn't mean it's the same as division by C because there is no operation called division. Okay, keep it in mind. Okay. In inverse, why do we need to interchange that values and all that is what Vyas is asking. Okay. Vyas P. See, to find inverse, where A, B, C, D, we just need to find a capital B such that AB is equal to I. Now, it happens that one convenient capital B is what we already guessed. I'll just put this in the next page because quite a few doubts have come beyond what I thought. And if capital B is 1 by AD minus BC minus B minus C, AB turns out okay, Amrit Narayanan, is there something called A power? Sorry, Amit Narayan. So something like A power minus 1 when A is a real number. Well, for A in n is an integer, yes, A power minus 2 is A power minus 1 whole squared is A inverse into A inverse. Some people use that, but it's not too common. Okay. Okay, I think that answers all the doubts. Let me now come to the question. The number of such matrices which have inverse. Okay. Now A, B, C, D belong to 0 comma 1. That means A is 0 or 1, B is 0 or 1, etc. Now how many such matrices have inverse? In order to have inverse, AD minus BC not equal to 0. Okay. Now let's consider cases. Okay. Cases. Now if A has 4 zeros, then determinant A is 0. Remember, determinant A is AD minus BC. Therefore, no matrix possible, no matrix with inverse, because if determinant is 0, inverse does not exist. If A has 3 zeros, whichever A put determinant A is 0, again no A, because whichever 3 places you put 0, it will become determinant 0. If A has 2 zeros, then okay, what are the cases that have determinant as non-zero? If you put 0 0 1 1, this won't work. So actually you have to put 0 0 1 1 or 0 0 1 1. Remember, two zeros means the remaining are ones, and two ones. Two zeros means and two ones. If A has 1 0 and 3 ones, all possibilities will give determinant, sorry, 1 0 and 3 ones, determinant will always be -1 or 1, plus or minus 1, and then 1 1 1 0. Okay, 1 0 and 3 ones. A has 4 ones, no A will have A inverse. Okay, so how many do we have? We have 4 matrices that have 3 ones. See, because there are only, it's possible to have all 4 zeros, 3 zeros, 1 1, 2 zeros, 2 ones, 1 0, 3 ones, or 4 ones. 4 zeros, not possible. 3 zeros, not possible. 2 zeros, yes, 2 matrices. 2 is the count. 1 0, 4 is the count. Correct? Are you able to understand? Okay, so this means there are 6 matrices. This is what I am getting. Okay, but many people have got 8. I don't know how you got 8. Okay, okay, Kajol, can I explain inverse using an example? I'm going to come to that. So therefore, there are sorry 6 matrices whose entries are a subset or belong to 0 comma 1 and whose inverse exists. Okay. Kajol, it was explained last class itself. Okay, just take a simple 2 by 2 case. Inverse for, let's just take inverse for A is equal to 2 3 4 5. Now determinant A is 2 into 5 minus 3 into 4. This is called, this is just definition. I haven't taught you determinants because determinants we'll do next class. But we know that determinant A is defined as AD minus BC. Okay, if A is ABCD, determinant A is AD minus BC. It's just think of it as some new definition. Now inverse is, so this is 10 minus 12, which is minus 2. A inverse is 1 by minus 2. Swap 5 and 2 and put minus sign for this. This is how you do. And then A and A inverse. A times A inverse is 2, 3, 4, 5 times 1 by minus 2, 5 minus 3 minus 4, 2. So multiply first row with first column, 2 into 5 minus 3 into 4, minus 2. Then first row with second column, 2 into minus 3 plus 3 into 2, minus 6 plus 6, 0. Then second row, okay, red with first column, will give 4 into 5 plus 4 minus 4 into 5. That will give 0 because this is minus 4. And then second row with second column will be minus 12 plus 10, which is minus 2. Okay. But there is a scalar outside, which is 1 by minus 2, which is simply 1001. So we have learned how to find inverse only for 2 by 2 matrices. Okay. I hope this is clear. Just give me 1 second. Sorry, I was just checking some other doubt. It doesn't seem like that's a problem. Okay. If that's clear, go ahead with question 12. Please go ahead and do question 12. Quite a few have finished answer 12. Very good. Okay. Okay. So we have 3a cube plus 2a square plus 5a plus I is null. Then what is A inverse? Well, given 3a cube plus 2a squared plus 5a plus I is null, we can write 3a cube plus 2a squared plus a is minus I. And you can write this as a times 3a squared plus 2a plus 5I. Please note this has to be 5I and not 5. A into 5, okay, is a scalar. But if you do a into a plus 5, not valid, because 5 is a scalar and a is a matrix. You can do a plus 5I. That's okay. Equals minus I. So a times minus 3a squared minus 2a minus 5I equals I. Therefore, this happens to be A inverse by the uniqueness. Therefore, by uniqueness property, minus 2a minus 5I is A inverse. I hope this is clear. Okay. Now let's move on to question 13. Again, we are learning about properties of inverse before we learn how to find inverse for complicated matrices. Just with 2 by 2 we are doing. Well, it turns out that this particular thing A inverse happens to be KA. Robin Bijo has asked a good question. Yes. And the answer is it possible to do question 12 by post multiplying the whole equation by A inverse on both sides? It's a good question. Okay. Which equation? You have to do this equation. Okay. So, what you are saying is post multiplying by A inverse. Okay. Sorry, not post multiplying. If you are doing post multiplying, yeah. So you are doing 3a cube plus 2a squared. You can do pre multiplication also, it won't make any difference. Minus I into a inverse. So multiply each term because distributive laws holds good. I think I mentioned this. A into b plus c is ab plus ac is true for matrix multiplication plus addition combination. So 3a cube into a inverse is 3a squared plus 2a plus 5i is minus a inverse. Therefore, a inverse is minus of 3a squared plus 2a plus 5i. But you can also pre-multiply by a inverse. But the only challenge is this statement, whether post-multiplying or this assumes a inverse exists. See, the question said find a inverse. So you can assume it exists. But suppose the question is find whether A inverse exists, and if so, find it. This statement is better. There is no pre-multiplication by A inverse. This statement proves the or this equation proves the existence of A inverse and finds it. See, A into something is I is enough proof to say that A inverse exists. But without knowing that A inverse exists, if you say I'll multiply by A inverse, then there is a small problem that you have. You don't know whether what you're doing is valid or legal. That's what would be my small objection. But to find the value, this is fine. I hope you are able to appreciate the nuance here. Technically, multiplying by A inverse means you're already assuming that it exists. A matrix, if it doesn't exist, how can you even multiply both sides? Okay, so that's a question that will come. But anyway, now let's come to question 13. Okay, you have A inverses. So we know determinant A is 2 into minus 2 minus 3 into 5, which is minus 19. Therefore, A inverse is 1 by minus 19 minus 2, 2 minus 3 minus 5. So this is equal to 1 by 19 times 2, 3, 5 minus 2. Therefore, K is 1 by 19. Answer is option B, fairly straightforward. Okay. Okay. The next question, okay, asks you what is the inverse of a skew symmetric matrix. But before that, I want to prove one statement, which is that, uh, okay, this is there in transpose. Okay. Okay. This is a very important statement. Okay. So, if A is an invertible matrix, that means A inverse exists, then A inverse transpose is A transpose inverse. A very important idea that you can swap transpose operators and will get the same result. If you're doing both operations on a matrix, Okay, how do you prove that? Okay, this is an important this thing. Okay, let's see if we can try and prove. Okay, so A is a square matrix. Okay, let B is equal to A transpose and C is equal to A inverse. Okay, let me see if I am taking the correct thing. Then to prove C transpose is equal to B inverse. Correct? This is what we need to prove. Okay, that means this implies or to prove that C transpose B is I. Correct? Okay. Is that correct? Correct. Or to prove C transpose A transpose is I. This is AC the whole transpose is I. Okay. To prove AC is equal to I, which is true because C is A inverse. So, alternatively, you can start from this. We know C is equal to A inverse. Therefore, AC is I. C trans taking transpose both sides. Just you can do the reverse steps. Both sides, you get C transpose A transpose is I because I transpose is I. Okay. Now that means C transpose into B is I because A transpose is B. They just define B as A transpose and C as A inverse. See, A will have both the transpose and inverse, and they're not equal. We are trying to prove that doing inverse on the transpose and doing transpose on the inverse will give you the same result. Okay, that's what you're trying to show. C transpose B is I, therefore C transpose is B inverse. But what is C? A inverse. Or A inverse transpose is B is A transpose. Inverse, hence proved. I'm just saying, how did I come up with the right hand side statements? Because I wrote the left hand side things. Okay, I hope you are able to see. This is a proper proof. Okay. Yeah, just give me 1 second. Just give me 1 second. Yeah. So now what we can do is try and do question. So that means you have some idea of what how to deal with inverses and transpose. Define a new, okay, matrix where necessary. That's what I have done. Okay. So please go ahead and do question 14. Inverse of a skew symmetric matrix. What is a skew symmetric matrix? Remember, skew symmetric matrix A is such that A transpose is minus A. Okay. What can you say about the inverse of a skew symmetric matrix? That is the question. Okay, quite a few have got it, but a few people have made a mistake. Okay, skew symmetric matrix is such that A transpose is minus A. Okay, now inverse of a skew matrix. So we need to find what about A inverse, right? So let A inverse. See, what did we do? A inverse is B or C. A inverse is C. A transpose is B, which is minus A. Now, is A inverse symmetric or skew symmetric, etc.? We have to find A inverse transpose. Symmetric or skew symmetric. We need to find A inverse transpose or C transpose. Okay, but we know A inverse transpose is A transpose inverse, just the result that we learnt. Okay, therefore C transpose is A transpose inverse. But what is A transpose? A transpose is minus A the whole inverse, which is minus of A inverse. But A inverse is C, so which is minus C. Therefore, C is a skew symmetric matrix. Okay, which gives us sorry, just give me 1 second. C is a skew symmetric matrix, which is option B. Okay. Okay. Now, Ayushman Podar has asked a doubt. I don't understand which question. But doesn't it depend on the order? Because if it's 3 by 3 order, any odd order, that's why the question says, yes, you are right. Um, you are right. That's why the question says if it exists. Okay, that means we are only talking of even order. The question says if it exists, it is Q symmetric. If it doesn't exist, we can't even talk about it. Okay, I'm going to come to that. In fact, I didn't talk too much about symmetric and skew symmetric other than the basic definition and this thing. Okay, I am going to come to that. Okay. um, Okay. Now, yes. Okay. So let me now come to how to find inverse. See, there are many ideas in matrices where we may have to go a little bit of back and forth. Okay. Shreya Kulkarni, this is a good point. In fact, I'm going to talk of one such confusion. Okay. If you do matrices and determinants, there is some, is there a way to get out? Yes, there is. I'll explain a little bit. Okay. Pamula Pravalika, where do we do pre-multiplication or post-multiplication in order to solve matrix equations? I think you have to see last classes. For example, if ABX or AXB is equal to C, we write AXB into B inverse is C into B inverse. So, so this can be written as AX into BB inverse because of associative property. BB inverse is I. AX is CB inverse. A inverse times AX is A inverse times CB inverse. This is pre-multiply by A inverse if it exists. This is post-multiply by, in the same equation I'm showing you both pre-multiplication and post-multiplication. The idea is if AXB is equal to C, then X is A inverse C B inverse. Okay, because of these steps. So if AXB is equal to C and A inverse B inverse exists, this is the main purpose of inverse itself. You can solve equations that have matrices. Okay. Shreya Siddhant, sorry, not Siddhant has asked, can I, is this fine? No, no, because question is for general. 2 by 2 is too specific a case. How do we know when to pre-multiply? Depending on what you need. See, it's like asking, how do I know that I have to divide both sides of this equation by 3? Because you have 3x, you have to divide by 3. So the answer is based on what is needed. I can't say in general, this is what you should do. This is, can we say Ka the whole inverse is Ka inverse? No, 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 no. Okay, in fact, that statement has been given in your this thing. You don't have to. Okay, Ka inverse, it is given as number 4 in properties of inverse. It's K inverse, A inverse. Ka the whole inverse. Example, 2a the whole inverse is half A inverse. Why? 2a times half A inverse is 2 into half times A inverse, which is A inverse, which is I. Therefore, this is the inverse of 2a. This is how you'll have to prove. See, inverse with multiplication is not that trivial. Okay. Please note, inverse of Ka is not K times A inverse. Okay. Transpose of Ka is K times A transpose because K is a scalar. But Ka whole inverse is not equal to Ka inverse. In fact, but when it comes to matrices, by the way, ABC whole inverse is C inverse, B inverse, A inverse. Everything gets reversed. Same thing happens when transpose. So inverses and transposes share some properties. but they also are different in properties like this. Like product of two matrices that transposes product of the transposes in reverse. Same thing, product of three matrices, their inverses. Take the inverse and put the product in reverse order. Okay, but some properties don't have equivalence. Keep that in mind. I hope this is clear. Okay, okay. Sagar Sinha has asked, okay, for question number 11, either AD equals 1, BC is 0, or AD is 0, BC equals 1, where both can be chosen in four ways. How four ways? Wait, that I'm not able to see. See, AD equals 1, BC equals 0 means A equals D equals 1, either B or C or both equals 0. Correct? So there are only three possibilities. B is 0, C is 1, B is 1, C is 0, B is 0, Z is 0. So that means 3. So AD equals 1, BC equals 0 has three possibilities. AD equals 0, BC equals 1. So 3 plus 3 equals 6, even by your logic. Where did you get four ways, Sagar Sanna? But it's a good thing where you have tried to find out directly when matrices are invertible rather than like the cases that I did. Okay, I'm glad you have tried something like that, but do clarify on what I've said. Okay, if not now, when we enable YouTube comments, you'll be able to type there, and I'll be able to see more easily and quickly. Okay, okay. Now the next idea that's there in the theory, but I've not given any question based on that, is that if a square matrix, if A is a square matrix, every square matrix A can be written as A is equal to, where P is symmetric and Q is Q symmetric. And this is important. Okay. And it's easy to find P and Q. P is simply A plus A transpose by 2, and Q is A minus A transpose by 2. P is symmetric because P transpose is A transpose plus A by 2, which is P, and Q is Q symmetric because Q transpose is A transpose minus A by 2, which is minus Q. I hope you are able to see this. It's a very beautiful result. Any square matrix. Okay, so if you write, for example, 2, 5, 3, 1, this is not as this thing. Let's say this is A. A transpose is 2, 3, 5, 1. P is 2, 4, 4, 1. And Q is A minus A transpose 0, 2. Sorry, I have to divide by 2. 2, 4, 4, 1. Oh, I did the divide by 2. Sorry. Yeah, yeah. 2, 4, 4, 1. 0, 1, 3 minus 1, and 0. Okay, and A is P plus Q. Pretty cool idea that every square matrix can be split into a symmetric plus q symmetric matrix. Okay, you can see that here. But and finding and showing that this is always possible is easy, because you can always find p and q as a plus a transpose by 2 and q as a minus a transpose by 2. But the challenge is, I have not just made this claim. Okay, I have actually made a claim that a square matrix A can be written uniquely as p plus q. Okay, no other A equals symmetric plus q symmetric. How to prove this? Okay, solve this question now. Okay, if you are able to prove, let me know. Just give me the outline of that proof. Okay, if you are not able to prove, that's okay. Okay, this is an optional thing. If you are not able to prove, that's okay. Just wait, I'll show you. Okay, you can think about the idea. Okay, so what I've shown, okay, is that every square matrix can be written as symmetric plus q symmetric. In fact, this is what books will tell you. From what I remember, many of the books will not tell you that this is unique. There is no other way to write a matrix as symmetric plus q symmetric. Why is that? Like, I didn't ask you if it's unique. I'm telling you it's unique and asking you to prove it. What I'm asking you and what I'm showing you is a more powerful result. Your book, okay, will generally tell you that any square matrix can be written as sum of symmetric and skew symmetric. Not just your NCRT book, but many textbooks will just tell you. I hope you are able to see that what I am claiming in the theory is a far more powerful idea, which needs justification. You can post the response of your proof in any way. Okay, whatever way you can, as long as it's legible. And I'll wait for a couple of minutes. If not, I will show you the answer, no problem. Okay, it's a hard question, that's why it's marked as challenge. Okay, and that's why I said that if you're not able to prove, that's fine. This is part that I'm asking you to prove. Okay, wonderful. Shreya Kulkarni has given the right answer. Excellent. Excellent. Rishikesh Rupesh Raghuvaran has also given. Excellent. Rakshana has also given. Excellent. So some people have just said there's only one way. That's not what I asked. Okay. Harinya Srinivas has given the proof that I have written as in what I was going to write. Okay. So let me state that. So Harinya Srinivas proof is what I'm actually giving. Okay, because this is what I would actually write. Let there be another way to write A is equal to R plus S, where R is symmetric and S is skew symmetric. Now we need to show for uniqueness that R is equal to P and S is equal to Q. Correct? I hope this is clear. Okay. Now let's now write the proof. Given A is R plus S, R transpose is R and S transpose is minus S because S is Q symmetric and R is symmetric. Now A transpose is R transpose plus S transpose, which is R minus S. And so A is R plus S, A transpose is R minus S. Adding 1 and 2, 2R is A plus A transpose, which means R is A plus A transpose by 2 is equal to same as P. Equation 1 minus equation 2 will give 2S is A minus A transpose. S is A minus A transpose by 2, which is Q, hence proved. Once you see the proof, it will seem very, very obvious. Okay. The others who have given the proof are Piyush Mishra, Avani Lakshmi Udupa. Okay. They've all given the proof by contradiction is the best way to prove. Okay. Actually, the operations here are fairly straightforward, but the thinking that you can do it uniquely and that you can prove it this way is a very important kind of thinking that I want you to develop. Okay. And to be very, very honest, upfront, when I say it seems daunting, how do you know it's unique, etc. But the operation is very simple. Okay, proof by contradiction is fairly simple. Okay, but I hope you are able to follow. Okay, so this is. I think if you are able to deal with questions like this, you'll be more comfortable with transpose, skew symmetric, symmetric, etc. Okay. Okay. Now, the last idea before the break that I want to do is the idea of finding inverse using elementary row operations. Okay, this is there in the online lesson. Okay, I have uh, explained how to do it. Your textbook also explains it. Okay, so what I'm going to do is I'm just going to do it just for one question. Question 15 I will do. Okay. Okay, I will do this question. If A is equal to, then find. If you know it already, if you have learned the online lesson and you can do it, then you can solve it yourself, but you don't have to submit the answer. You can just verify it with what I give in the end. Okay. Um, just give me 1 second. Just give me 1 second. Okay. See, if you want to find A inverse, what does it actually mean? Okay. Sorry, before that, there are a couple of questions. That's what I was just checking. In question 13, won't determine a change minus 19 to positive 19. No, it is okay. So in question 13, okay, in 13, the determinant will change. See, it's 1 by 19 times original matrix A. Determinant is minus 19, minus 1 by 19, but it's minus 1 by 19 times. The inverse is minus 1 by 19 times something. So, yes, that's why it becomes positive 1 by 19. That's why the answer is option B, Kavya Karthik. Amita, the inverse of a matrix using elementary operations is a bit hard. So, use a method where I take a matrix A and another matrix B, filled with only variables. Amit, actually, I'll give you a better method earlier. Adjoint method is easier or harder than elementary. Adjoint is easier. Sanjana Vijay Krishnan has asked, is there something like commutativity or associativity with inverse, with transpose and inverse? Okay, yes. So for transpose, A, see, it depends on what operations. A transpose into B transpose not equal to B transpose into A transpose. But what do you mean by commutativity? Are you saying A plus B the whole see, depends on what transpose is on a single matrix. Commutativity, associativity is on two or three matrices. If you are asking, is this true? But this is not commutativity of transpose. This is commutativity of addition. Correct? So I don't know exactly what is the question. Multiplication is obviously not commutative. Okay, see, transpose and inverse. On a single matrix. We did say that A transpose inverse equals A inverse transpose. So if you take both these operations, the order doesn't matter. It's a little bit like commutativity, but it's not commutativity. Commutativity has to be on two matrices. Okay, one operation on two matrices. Here you are doing two operations on one matrix. Does not come under commutativity. Sanjana Vijay Krishna. Okay. Okay. Now I will do the row operations part. The other part we will see. First, what are elementary row operations? Okay. Um, I just want to use the same notation that, okay, so if we have an equation like A equals BC, then doing the same elementary row operation on both sides, okay, or sorry, on A and B, preserves the equation. Now, what do we mean by, okay, elementary row operations? Okay, list of, okay, this is fairly straightforward. Interchange any two rows. So that means Ri becomes Rj. Okay. Then multiply any row by a non-zero number. By a non-zero number k is Ri becomes Kri. And finally, adding any row to the elements of another row. This means Ri becomes Ri plus Rj. Now, these three operations are called elementary row operations because if you have an equation A is equal to BC, after applying elementary row operations, in fact, let me just call it ERO, elementary row operation on both A and B, we will get A1 is equal to B1C. Okay, and it will be true. If A equals BC, then A1 will be equal to B1C. That means equation is preserved. See, if you multiply A by 2 and B by 3, 2A is not equal to 3BC because A is BC doesn't mean 2A is 3BC. In fact, it's wrong. Equation is not preserved. The equation's validity goes for a toss. But you're not going to do things like multiply A by 2 and B by 3. If you do the same swapping of both rows, the idea is BC is a multiplication operation. But if you change two rows, the results rows will also change in the same way. So think of A as BC. If you swap two rows in B, then A's rows will also be swapped. So if you do the same row operation on both, the equation is preserved. Same holds good for Ri is KRi and Ri is Ri plus Rj. If Ra becomes Ra plus Rj in B, the net result of this operation is that in the final answer A, because B into C is the operation we are doing, in the final answer also the ith row will now become ith row plus jth row. Now, proof of this is sort of intuitive. If you want to do it systematically, it's messy. It's possible, it's just messy. But in fact, you don't even need the proof. Your book does not even give you this level of intuition. It just says do the row operation, by magic inverse will come. I'm trying to tell you what that magic is. If you start with the matrix A is equal to IA, do elementary row operations to write I is equal to BA, where A goes to I and I goes to B. That means from A, try to get I. So you will get I is equal to BA, and then what is left in the end is your inverse. So then in the end, what we have B is A inverse. This is what is the power of elementary row operation. Let me just finish with this question, and after that we will have a break. Okay. Now, some people find elementary row operations difficult. It's okay, not a problem. Okay, but last class also somebody asked, so I'm just doing it just for this thing. Okay, you can use it as a checking method. Okay, just in case. So what do I mean by I is equal to BA? That means, so we start with A is equal to IA. Okay, so your original matrix is 3 minus 3 4, 2 minus 3 4. I hope there is nothing special about this matrix. Okay, 3 minus 3 4. Okay, it is not. It's not special. It's in fact a nice matrix. Okay. Okay, think of this as this equal to 1 0 0 0 1 0 0 1 1 times 3 minus 3 4, 2 minus 3 4, and 0 minus 1 1. Okay. Now, what do I want? I want to get, okay, zeros. I want to become, so the steps that I want to do are try to get zeros in second row and third row beginning. Okay, in the first column. Because if you want to change A to I, you must have zeros. I will have many zeros. Beautifully, this zero already exists. So to make 2 as 0, what do I need to do? Well, I might need two steps. Okay. First, I might have to multiply this by I can directly multiply by 2 by 3, etc. But that will be very messy. Instead, let me just multiply it by 3. 3 minus 3, 4. 6 minus 3, 12. 6 minus 9, 12 equals 1 0 0 0 3 0 0 1 1 times this. I'm not going to write the A matrix again and again. It's all A. Because you, remember, you do the elementary row operations on only two of the matrices. The third one is just A. Okay, and what we have done is these two we have multiplied by, so the operation we have done is, let me write it in a, so R2 is equal to R2 into 3. It's a row operation. Okay, next, okay, we do 3 minus 3 4. You do from 6 minus 9 12. I'm going to do this minus 2 times R1, so you will get 0. But minus 9 plus 6 will become minus 3, and oh sorry, this will be 12 minus 8 is still 4. See, what I've done is and 0 minus 1 1. I'll tell you what is the operation I have done. This is 0 minus 2 times is minus 2. So here what I have done is R2 minus 2 R1 so that I get a 0. My goal was to get this 0. Okay. Next, what I need is uh, I think I got zeros in the first two columns. The first column and second and third row. Next, I need to get 0 in A32. This fellow, try and make it into 0. So again, I'll do two steps. First, multiply this by 3, and then I can subtract, like R2. So I can do 3 minus 3, 4, 0 minus 3, 4, 0 minus 3, 3. So I'm going to do the operation R3 to R3 equals 3 times R3. So this will be 100 minus 230 033A. Next, I'm going to do the operation R3 is R3 minus R2 because this was my goal. See, instead of multiplying by fractions, I'm just doing 003. So I have got, so this will be 203 minus 230100. Okay. You have to follow a bit carefully. It's a lot of steps. Okay. But sorry, this is, wait, there's a small mistake I made. When I did R2 is minus 2R1, I did a mistake. It's 230, and this became, sorry, when I did it's R2 into 3. Sorry, this was not 0. Okay, this is 001. Identity. So this would have 003. Okay, sorry, I made a small mistake. I just realized. This will become minus 2 minus 3 3. Yes, Lakshmi Avani Udupa has also said that there is a mistake in the first step in writing identity itself. Yeah, I just realized it. I just saw that there's a mistake everywhere, but it's a simple thing. I corrected it. Okay, R3 is R3 minus R2 is what I have done. Okay, see, you can think of this as step. This is step 1. This R2 is R2 into R3. Step 2, step 3, step 4. Okay, so this, okay, let me just call this with some capital Roman letter 1 2. Okay, so this has happened in steps 1 2 and 3, and 0 and A32 has happened in 4. Correct. Next, we need to get A13 and A23 as 0. Okay, that means in the top, sorry, the third column, first row and second row, we have to get a 0. Okay, so how do we get? Well, first thing is, if we just do R2 is Uh, I think you can just do R2 is, see, but remember, you cannot do R2 is R2 minus R1 because then you will lose the existing zeros. You can now do it only with R3 because R3 has zeros already. So the operation that I will do is R2 is R2, okay, R3 minus R2 will give, sorry, once last step, R3 is R3 minus R2 will give 0 0 minus 1, I think. It's not this, this will give minus 1. Now I do R2 is equal to R2 plus 4R3. So this will give 3 minus 3, 4, 0 minus 3, sorry, 0 minus 3, 0, 0, 0 minus 1, 1, 0, 0 plus 4R3. So this will be 8 minus 2 will become 6. Then this will become minus 9 and 12. Okay. It is definitely cumbersome. Okay. The next step I'm going to do is R1 is R1 minus R2 because that will give me a 0 in the, sorry, R1 is also R1 plus 4R3. First I have to do that. So that will give me 3 minus 3, 0, 0, 0 minus 1. Okay. Uh, 4. So 9 minus 12, 12, 6 minus 12, 2 minus 3, 3. Okay. I think the last step is just to get one more 0 here. Okay. R1 is R1 minus R2. So 3, 0, 0, 0 minus 3, 0, 0, 0 minus 1 is what I will get. R1 is, of course, the A is there everywhere. I don't have to bother. Okay, so you get 9 minus 12, 12 will become 9 minus 8 is 1, 3, sorry, 9 minus 6 is 3, minus 3, 0, 6 minus 9, 12, and 2 minus 3, 3. Okay. No wonder people felt this is cumbersome. So these steps you can change step 1, 2, 3 and step 7, 4, 5, 6, but broadly it will be the same. Now I need to get get rid of the threes, so I can do it in one shot. Okay, just to save the R1 is R1 by 3 and R2 is R2 by minus 3 and R3 is R3 by minus 1. If I do all of these, I don't want to write it as three separate steps. I'll get 1 0 0 0 1 0 0 0 1. Just remember to do it clearly. R1 by 3 will give 1 minus 1 0. Then R2 by minus 3 will give minus 2 3 and minus 4. And R3 by minus 1 will give minus 2 3 and minus 3. And lo behold, we have I is equal to BA, and therefore B is A inverse, which means A inverse is the last matrix that we found. And you can check that this matrix, of course, I have chosen it in such a way that you don't have ugly fractions because that will make it much worse. 3 minus 3, 4, 2 minus 3, 4, and 0 minus 1, 1 is 1 0 0 0 1 0 0, sorry, 0 0 1. Let's check. 1 into 3 minus 2, 1, minus 3 plus 3, 0. So I'm just checking that you are actually getting the identity if you multiply. So this is A inverse times A is I. Okay. I know we took quite a bit of time, but there is no shortcut for the row operations. Okay. For now, just ask any doubts in the row operation. After that, we'll go for a break. Okay. So get A13 equals A23 equals 0. I've got it in steps 5 and 6. And then in 7 and 8, we got A12 equals 0. So this is 7 and 8. And finally, I equals 1 is 9. Is there a 9? Sorry, that was step 7. Sorry, that was 7 only. And this is 8. So just look at this. The steps that I did are towards this goal. I didn't randomly come up with R1 is R1 plus R2, etc. This is the goal. The goal is first get zeros in second and third row, first column. That means I wanted these two zeros. Okay, I got it in 2 steps or 3 steps rather. Okay, did we need 3 steps? Steps 1, 2 alone, right? A3 to this is 3 and 4. Sorry. Two steps, I got 2 zeros. Then 3 and 4 was focused on this becoming 0. Then 5 and 6 was focused on these two becoming 0. Notice how I first multiplied by something and then this thing. And then 7 was focused on this fellow. And then 8 was focused on each of these diagonal elements. Okay. Ananya Sur, can you apply this on do column operations? Yes, but you'll have to change the equation. Okay, it is not a common thing. Technically, see, you have to write this as A is equal to AI and then something like that. Okay, keep this A and make this into B. Okay, so then you will get I is equal to AB, so A B will be A inverse. Because if you change the column thing in I, the column in A will be affected. That's how. Okay. Adityan, is it okay if we are not comfortable with row operations? Is there any place where only row operation? No. Okay. Yes for the first question, no for the second question. JE does not need row operations. I'm doing row operation, okay, only because it's there in your school syllabus. Have they removed it? If they have removed it, then it's a waste of time that I did. Okay. I think somebody also asked me. The answer is yes. Because somebody also asked me how to find inverse. There are 2 ways of finding inverse. One is row operations, the other is the adjoint method. I'm going to show you the adjoint method shortly. Okay. Okay. So let's take a break now. Okay. Already when I did row operations, some people took a break, meaning that I'm not going to do it. I just wanted to take that 15-20 minutes to just cover it once and for all. Okay. Yeah. Siddhant Hola broadly did the thing. First do zeros using RA minus KRV, then get the ones using RA is equal to KRA. Correct. Is there an operation like this? No, because this will mess up the matrix multiplication part. That's why. Sriniyati Saravana Kumar, is it okay if you are not comfortable? Yes, it's okay. I've answered already a couple of times. Many people have asked. Okay, so let's take the break now, and after the break, we will start with worksheet 2 on adjoint and other ideas. Shraddha, okay. Basic objective is to make the matrix on the left an identity matrix using row operations. Yes. Do row operations work on non-square matrices? Technically possible. I don't want to go into that, but it can work. Okay, because the original idea, what is interesting about row operations is actually not the steps because they're very tedious. What is interesting about row operations is the logic that A1 is equal to B1C still holds. And that is actually very beautiful. Okay, A is equal to BC. That is what I would like you to have as a takeaway from this entire row operation. That's the thing that the books don't cover. A is equal to BC. Why does row operation preserve the validity of the equation? Think about that. That I think you should be comfortable because that may be useful for solving some JE questions. Okay. Okay. Let me take the break now that I've been saying for the last 10 minutes. We'll be back in 5 minutes. Okay. Okay, break over. Please come back. Please come back. Break is over. You just see. Okay, so now let's come back. I originally thought I'll give two breaks today, but I gave one break of a longer duration. Okay, now we are going to move on to worksheet 2, okay, which also has been shared with all of you, I hope. Okay, now this, the theory for this has not been done in the online lesson, I think, because it's also a little harder. Okay, uh, which is why I was wanted to finish whatever has been done in the online lesson. Okay, just give me 1 second. Okay, so we are going to start with what is known as adjoint of a matrix. Okay, and the very first thing, okay, what is adjoint of a matrix? Adjoint of a square matrix. If A is Aij n by n, adjoint is given by adjoint of A. Adjoint of A is C transpose, that is equals transpose of the cofactor matrix. C is cofactor matrix. So think of adjoint A is equal to transpose of cofactor matrix of A. Okay. What is cofactor matrix? This is the first question. It's a new matrix. First of all, cofactor matrix is a new matrix. So C is equal to Cij n by n, where Cij is minus 1 power mi plus j times mij. What is this mij? Mij is the determinant of the submatrix. It's also there in the theory. Element Cij is obtained by this thing. Okay, so the first thing is, some people said that sir, row operations are very complicated. Okay, and now YouTube comments have been eliminated. Be responsible. Ask doubts only about what is being covered. Do not spam. Do not respond to other people's comments, etc. These are standard rules. Keep this in mind. Okay. But hopefully we'll be able to get to doubts in this thing faster. Okay. Okay. Now, so adjoint is a tricky idea. Okay. Okay. Please do understand that adjoint is tricky, and therefore I just wanted to do it in class. Okay. I could have done it in the online thing also, but then there'll be 100 different doubts and questions. Okay. But it looks complicated, but it's actually not that bad. It's tricky, but it's not too bad, is basically what I want to clarify in the beginning. All right. So let's start with 2 by 2 matrices. Adjoint will be very easy. Let's say A is equal to A, B, C, D. What is the, okay, what is M11? You eliminate first row and first column. Okay, you will simply get D. Determinant of the remaining matrix is D. Okay, M11 is D. M12 will be C. M13 will be, sorry, M21 will be B, M22 will be A. So the capital M matrix will be D, C, B, A. Now remember, cofactor is minus 1 power M I plus J times each of this. So for example, if it is M11 multiply by minus 1 power 2. So it will become D minus C minus B A. And finally, adjoint is transpose of, wait, transpose of cofactor. Adjoint A D minus B minus C A. Okay. So 2 by 2 matrix is very easy. You can directly C transpose. Many people directly go to cofactor. This is cofactor matrix. You can directly write instead of writing this minor. This step is often ignored, often skipped. Okay, that's why minor is a minor idea. Cofactor is a big idea. If you remove the row and column, whatever you get, that determinant multiplied by minus 1 power I plus j is what you will enter in the cofactor matrix. Okay, 2 by 2 is very easy. So for any now comes the beauty. Okay, if you do A times adjoint A, and this is what is the power of adjoint, you get determinant A times I. Do A B C D times D minus B minus C A, you will see that AD minus BC, okay, 0 0 AD minus BC. This is determinant AI. This is the power of adjoint. So adjoint is connected to inverse. Okay, of course, I haven't proved this for general this thing, which we won't be able to. That's beyond the scope of our course. That for any general matrix, that's what it will be. Intuitively, you can do some guess and this thing. Okay, I'll explain how to get that intuitive thing. Okay, so A into 1 by determinant A adjoint A is I. So therefore, A inverse is 1 by determinant A times adjoint A. This is the reason why I asked, how do I find inverse? Do 1 by determinant A times adjoint. But why did I talk about inverse first and not adjoint? Because inverse is easier to understand than adjoint, because adjoint has many steps. Find cofactor, transpose of cofactor, etc. Okay. Now let's do for 3 by 3 matrix that we just found the inverse. The same 3 by 3 matrix, you be the judge of which is the easier method. Okay. So our A matrix was, okay, this was the A matrix. Okay. And the inverse we found using row operations. Let's go back. This was the inverse. Inverse we calculated using row operations. Okay. Let's check. Inverse using adjoint. First, let's find the adjoint. To find adjoint of A, okay, we need cofactor matrix. Just 1 second. Okay, oops. Just give me a second. There's a small glitch. We need cofactor matrix. So we can write the cofactor of A Okay, cofactor of A is minus 1 power I plus j times the minus. So for example, the 1 entry, remove these two. What is left is this submatrix. What is the determinant of this? Minus 3 into 1 minus minus 1 into 4. So minus 3 plus 1 is 1. But 1 into minus 1 power I plus j. But that will keep swapping, changing from 1 to minus 1. Minus 1 power 1 plus 1 is 1. So that's simply 1. Okay. So suppose I want to find the entry corresponding to first row, second column. Okay, remove those two. You get the remaining determinant is 2401. Determinant is 2. 2 into 1 minus 4 into 0. Just look at the 2 by 2 as it is and write the determinant. But then you have to multiply by minus 1 because 1 comma 2. See, C1 2 will be minus 1 power 1 plus 2 M1 2. So it's minus of the minor. Minor is basically the determinant that you have left if you remove the row and column. Okay. Now C13 will be plus, C21 will be minus. So if ij is such that I plus j is odd, you will get minus. So it's minus 2. Then go to 3n, determinant is minus 2, and this is, so you have to put plus, no multiplying by minus. Okay, next, 2 and 1, determinant is minus 3 plus 4, which is 1. Okay, then 2 and 2, determinant is 3 minus 0, so it is 3. Okay, oh sorry, 2 and 1, did I multiply by minus 1? I don't know, maybe I forgot. Determinant is minus 3 plus 4 is 1, and I have to multiply by minus 1 because it's minus 1 power I plus j. So this comes with the minus. So that's what you have to just be a little careful. Then 3, then for the now, by now you don't have to strike, you can just look at the remaining and write the determinant. 3 minus 3 plus 0 is what I will get, and I have to now this is 2 3, so it will become plus 3. And then finally, so if I remove this fellow, I'll get minus 12 plus 12 is 0. If I remove this fellow, determinant is 0, there's no plus or minus. 12 minus 8 is 4, and it's 2 3, so it's minus 4. And the last one is minus 9 plus 6 is minus 3, and minus 3, and it's just no change. Okay, transpose of cofactor, adjoint A is cofactor of A transpose. So this becomes 1 minus 1 0, minus 2 3 minus 4, and minus 2 3 minus 3. Now one, obviously one extra factors, to find inverse you have to find determinant. And determinant A, if you don't know, you, okay, determinant A is, by the way, in fact, cofactor and determinant are connected. So if A is A31, A32, A33, determinant A is A11, C11, cofactor matrix 11 plus A12, C12 plus A13, C13. That means if your A matrix is given 3 minus 3, 4, remember this is the A matrix. First row is 3 minus 3 and 4. Take the first row of this. 3 into 1 minus 3 into minus 1. Oh, sorry, I shouldn't do the transpose. I should do it with the cofactor, which is this. 3 into 1 minus 3 into minus 2 is 6 plus 3 9, minus 4 into 2 8. So you simply you will get 1. And the beauty is you can write determinant A as A21 C21 plus A22 C22 plus A23 C23. You can write determinant A as any row times its corresponding entries in the cofactor. And this is not very difficult to see. For this, you need to know what is determinant, but then determinant is defined this way. So I cannot prove it. If I define determinant this way, I cannot prove it. So you will see that there's a little bit of going back and forth. Determinant is defined using cofactor. Okay. And determinant and cofactor are used to finding inverse. So there's a lot of back and forth that we go. Okay. So, and I'm not giving you proofs also, and I'm stating that clearly upfront. Okay. Just keep that in mind. Okay. Okay. I hope this is clear. Okay. So this, and because determinant A is 1, here the inverse is the same as the adjoint. A inverse is 1 by, so here in this case it is the same as here. For this example alone, adjoint A is the same as A inverse. And then, and we have beautifully calculated that this inverse matches exactly with what we got in the row operations. 1 minus 1 0, minus 2 3 minus 4, and 2 3 minus 3. Okay. So we, for the same matrix, we have found inverse using row operations as well as adjoint method. Okay. Okay. I hope this is clear. But the adjoint has some beautiful properties, which is that A into adjoint A equals adjoint A times A is determinant A, because adjoint behaves like inverse except for a constant, which is determinant A. Okay. Now, why should it be like that? For in general, any n by n matrix is a much bigger this thing. So that's why I said I won't be able to do that. Adjoint of k times a matrix is k power n minus 1. Now, why is that? Well, here we are going to use some properties related to determinants. See, if A is n by n, determinant of Ka, we will learn it more in determinants, is k power n determinant A. Why? Determinant is, if you multiply all the entries by a constant, determinant will get multiplied by k power n. See, determinant for 3 by 3 is, okay, so let's say determinant of 1 2 4 3 1 minus 1 2 0 1 etc. It is 1 times this determinant plus 2, or rather minus 2 times the determinant of 3 1 2 minus 1 plus 4 times 3. So it's 1 times 1 into 1 minus 2 times 3 into 1 plus 1 into 2 plus 4 times 3 into 0 minus 2 into 1. So it's 1 minus 2 into 3 plus 2 plus 4 into minus 2. So it's 1 minus 12 minus 8. So it's minus 19. Sorry, just a minute. Now, if you multiply, let's say 5a, 5a will become 5, 10, 20, 15, 5, minus 5, 10, 0, 5. You can see that every entry gets multiplied by 5. So the first term will become 5 into 5 into 5. So it will become 5, 125 instead of 1. So determinant of 5a is 5 cube determinant A if A is 3 by 3. If A is 4 by 4, it's 5 power 4. Now, this property we may learn later again in determinants, but it's an important thing. Hariprasad said, I don't understand the part where you use cofactor to find determinant, because that's how determinant is defined, Hariprasad. Multiply each element by its cofactor. A11 times C11, A12 times C12, A13 times C13. If you take all the three elements of a row, three entries of a row, and multiply each entry with its cofactor, you get the determinant. That's how you define determinant for 3 by 3 or 4 by 4 or 5 by 5. Remember earlier I defined determinant for 2 by 2. That was very trivial. AD minus BC, that's all. But the same idea applies there also. Write the cofactor matrix A times D and B times minus C. Okay. We are stuck with these two methods only, Abhinav Dilip. I'm glad you asked. These are the only two methods. These are the, in fact, cofactor method, I would say, is much faster. Once you become comfortable with cofactor, it will be very, very fast. Because you will use cofactor everywhere while you're doing determinants, while doing adjoint, etc. So cofactor matrix is something that you will just be able to write very quickly for 3 by 3. Now, thankfully, JE or no other thing is going to ask you for 4 by 4, because anything 4 by 4, let a computer handle. 3 by 3 is just to check whether you know where to put minus, plus, etc., and not get confused. Okay. Kajol, I'm confused how to find Mij, small Mij. Please remember, capital M is the matrix, small Mij is the entry. The way you do it is remove the ith row and jth column. That's what I showed step by step. No, you cannot take out K. Determinant of something. Okay. Determinant, that's what I'm just showing you. Determinant of phi A is not phi determinant of A. It's phi cube determinant of A. Is not equal to phi determinant of A. Therefore, determinant of, so adjoint also has the same this thing. It is adjoint of Ka is not K times adjoint of A. Adjoint of Ka, think about it. Adjoint of Ka, if you want, you can write it as see, adjoint A is A inverse times determinant A. We know. Okay. Okay, if determinant A is not 0, we can write this as adjoint A by determinant A. Adjoint of Ka is Ka the whole inverse, determinant of Ka. Ka the whole inverse is K inverse A inverse. Determinant of Ka is K power n determinant A. So K power n into K power minus 1 is K power n minus 1 A inverse determinant A, which is K power n minus 1 adjoint A. This is how the previous thing was derived. Adjoint of K times the matrix is K power n minus 1 adjoint A. No, this method is not there in the online lesson. That's why I'm trying to show. Maybe we will add it later, Manas, but it's a little confusing. That's why. Okay. The other lesson, it may be there. I will share it if it is there as an extra thing. Okay. But I didn't want you to do this before the class because there are many questions in this. Okay. That people, this thing. Vijay Srivatsan, can we write A plus B whole inverse is A? No. No. A plus B whole inverse is just like asking, can you do 1 by 3 plus 5 as 1 by 3 plus 1 by 5? It's like that because inverse is like 1 by 3, right? It's not exactly division, but it's like that. That's wrong. Okay, Vijay Sri. If determinant A is 0, yes, then A inverse does not exist. That is what we wrote earlier. Remember, when we defined inverse, I'm glad you asked this question, Hari Prasad. When we define inverse, we said determinant A is not 0, inverse is defined. And now you can see why. Because inverse is linked to determinant through adjoint. A inverse is adjoint by determinant A. If determinant A is 0, you cannot have inverse. Okay. I hope and then adjoint of AB is just like an inverse. Why? Because you can write this as adjoint of determinant A times A inverse. So adjoint of AB is adjoint of A inverse, determinant B, B inverse. Correct? A is, oh, sorry. No. What am I saying? I'm blabbering. Sorry. Adjoint of AB is determinant AB times AB the whole inverse. Determinant AB is determinant A, determinant B. This is a property I will not prove, but I will use it extensively. Okay. Keep in mind, this is a very, very useful property. The proof is too messy. Okay. In general, for any two matrices, the product of their determinant is the determinant of the product. And AB the whole inverse, we know, is B inverse, A inverse. Okay. Now you have to be careful. You can't just, so you can combine this and write this as adjoint B. So determinant A times adjoint B times A inverse. Now you can take the determinant A, because it's a constant, you can take it inside. Okay. And this becomes adjoint A. That's why adjoint of AB is adjoint B times adjoint A. It behaves a little bit like inverse because it's very closely connected to inverse. Okay. This is the theory related to adjoint. Let's start with some questions on adjoint. Okay. Find adjoint. If adjoint A, okay, adjoint A is this, adjoint B is this, find adjoint AB. Okay, do question 1 in the worksheet. Sorry, Mahargadas, you're confused too much. Adjoint A and determinant A cannot be inverse. See, determinant A is a number. Please remember, determinant A is a number. Inverse is a matrix, adjoint is a matrix. It's not square root or number or anything. Okay, you just got too confused because we've written a lot of stuff. Adjoint is, okay, determinant times the inverse. Determinant is a constant. Determinant of A is a number. It's not a matrix, it's a number. Okay. Adjoint of A is a matrix. If A is n by n, adjoint of A is also n by n. Matrix A, adjoint of A, inverse of A, transpose of A are all n by n matrices. Determinant of A is a number. It's not a 1 by 1 matrix, it's a number. One number. Sir, adjoint A is determinant A power n. My determinant of adjoint A, correct. Determinant of adjoint A is determinant A power n minus 1. I haven't come to that. No, there is no determinant A whole power n is not Yes, it's correct. It's correct. This is correct. Because I just showed product rule. Determinant of AB is determinant A, determinant A. So determinant of A square is determinant A, which is determinant A whole square. This is correct. Okay. I haven't come to all this, so just hold on a little bit because others may get confused. Okay. Determinant plus adjoint plus inverse are all intricately mixed up. And the common thread binding all of them is cofactor. You need cofactor for adjoint, cofactor for determinant, cofactor for inverse. Okay, generally cofactor is what you have to get comfortable with. Okay, I hope that part is clear by now. Yes, Siddhant, that's why. No, we still should have it in the online. It should, I mean, we could have it and not assign. But what happens is many people get thoroughly confused, get like, demotivated, and then I can't able to follow, etc. So we will put it. It's just that we'll need to be a little careful. See, also, I want you to understand that if you're comfortable with everything in the online lesson so far, the inverse, transpose, Q symmetric, symmetric idea, these things will become easy. Okay, you will become comfortable with doing all these operations. Okay, please, okay, let me see answers for question 1. I think this is fairly straightforward. Adjoint AB is adjoint B times adjoint A. It's 2 minus 6 minus 4, 8 plus 6, 14. This is more like a multiplication exercise. 24 minus 2, 20. We haven't given you A and B. I've given you adjoint A and adjoint B, and I've asked adjoint AB. So it's simply adjoint B times adjoint A. Let me just check if it is correct. Sorry, it's 2 minus 9. So it's minus 7, not minus 4. 8 plus 6 is 14. 6 plus 3 is 9. 24 minus 2 is 22. Okay, quite a few people have got minus 7, 14, 9, and 22. No, Hari Prasad. Yeah, that's what I just clarified. Marga Das, it's minus 7. You are right. I made a mistake. Uh, okay, don't put your answers in the comments because it will spoil it for other people. Okay, don't put your answers in the comments. Quite a few have submitted. Okay, now, so question 2 is where you have to seriously look at cofactor and all that. Okay, go ahead and do question 2 where you have to find adjoint A and then do A into adjoint A. Okay, please do question 2. No, Siddhi Vinayak, don't do any of these. Just do adjoint like transpose of cofactor. Don't do all that. See, right now I'm just asking you to do some straightforward work, Siddhi Vinayak. Okay. Yes, A inverse is I. So determinant of, you can use determinant operation. Yes, you can do determinant on both sides, but that won't help you to solve this problem. See, the YouTube part is only for asking doubts. The answer submission you should still do in the the chat box, the regular box that the mentors provide, because that's when we'll know that you have solved. I don't want anybody to put answers here at all, please, because that spoils it for other people. See, please note that YouTube is, the only purpose of YouTube is so that doubts can be asked, answered, clarified, response note, etc., can be done quickly. The YouTube chat is not actually meant for you to chat among each other or to replace the answering option, etc., because that spoils the entire atmosphere for other people. That's why I'm not using it for the full class. I've tried it 2 3 times, I've said it also. Okay, please use only the positive features of the YouTube chat, which is, if you're asking a doubt, it's easy for me to see, respond, and you can respond saying it is I understood, or you can give further clarification. Any other purpose you use it, commenting on other people's thing, etc., generally distracts it for other students. Keep that in mind. This is why whenever I do polls, many people say don't do YouTube chat. There are 5 10 people who dominate it and the rest get this thing. I would like everybody to have an opportunity to ask a doubt on YouTube chat and get it clarified. Okay, so your cooperation is needed to make YouTube chat more effective for the class as a whole. It is not just a tool for you to vent out whenever you want to say something. Okay, that is not how you should see it. Okay, I hope you, I mean, you're all 12th standard students, so I hope you can behave responsibly. Okay. Some errors you point out, I do 10, you say -10, etc. That's okay. As long as one person has pointed out and other people have seen it, it's fine. You 3 people don't have to point out the same mistake. Okay. Quite a few people have got it. Very good. Very good. So let's see. Adjoint A. First, let's find adjoint A. For that, first we need cofactor of A. Cofactor of A is, so I'm going to do quickly one by one. For this entry, 2 into 2 plus 1 into 5, 4 plus 5, 9, minus 1 power 2. So this is 9 itself. Okay. For the second one, okay, for this fellow, 0 minus 4, minus 4, and then minus of that. So it will become plus 4. And then for the third fellow, it is 8, and then it will be 8. Okay. I hope you are able to. Okay. And then similarly for the next, so it's minus 2 into 2, minus 3 into 5. So it's minus 4 minus 15 is minus 19. Then it becomes plus because there is a minus 1 power. Then the next entry is 2 plus 12, which is 14. Okay. And there is no change in sign. Then the next entry is 5 minus 8 is minus 3, and there is a change in sign, so it becomes 3. Okay. And then finally, for this, it's 2 minus 6 is minus 4. It will remain minus 4. Here it's minus 1, minus of that, so it will become plus 1. And the last one is 2, and sign will not change, so it's simply 2. So adjoint A is cofactor of A transpose, which is 919 minus 4, 414 1, 832. A into adjoint A equals 1 minus 2 3, 0 2 minus 1, and minus 4 5 2 times 919 minus 4, 414 1, and 832. So if you multiply, you will get 1 into 9, minus 8, 1 plus 24, 25. The other entries will be 0, 0. 9, 0 plus 28 minus 3. So this is what you will get. It's 25i. Therefore, determinant A is 25 is what you can conclude. And the way you can conclude it by taking each element of A, multiplying it by cofactor. So you see the multiple connections. So what you do is, suppose you take this row and multiply by elements of the cofactor matrix. 1 by 1 into 9 minus 4 into 2. So 9 minus 8 is 1 plus 3 into 8 is 25. But you can also do second column by second column. Determinant is so beautiful. Minus 2 into 4 is minus 8. 2 into 14 is 28. 28 minus 8 is 20. 5 into 1 is 5, 25. You can do third column into third column. See, once you have cofactor, you can do wonders, basically. Okay, I hope you are able to see that. You can multiply any row of the matrix with the corresponding entries in the cofactor matrix, like element wise multiplication. It's not matrix multiplication. It's not like take A into cofactor A. No, A into cofactor will give nothing. You have to do each element by each element and then add. Okay, I hope this is clear. Most people got it right. Okay, it's an important thing to understand. Good sources for, okay. I'll look and get back to you and give it to you, Rishikesh. Okay. I use A inverse is equal to 1 by determinant adjoint and pre-multiplication by A. Yes, if you find determinant A, you know A into adjoint A is 1 by, yeah, you can do that. But I asked you to verify it, Shreya. See, I wanted you to verify that A into adjoint A actually gives determinant A times I. That's what I wanted you to see. Okay. But anyway, okay. So now let's go to question 3. Please go ahead and do question 3. This should be fairly straightforward. Please go ahead and do question 3. Okay. If you have any doubts, you can post it in the YouTube chat as well as in the regular box. Okay, quite a few have finished, but there is a confusion. Yes, Manas, I'll try and do that. Okay. Okay, determinant of 2 times adjoint A. Okay. Oops. Sorry, I made a mistake. I should have given determinant of adjoint is 4. Okay. Then what is determinant A? Okay. See, I didn't give determinant. Okay. See, first. Okay. We know A adjoint A is determinant A times A inverse. Correct? Therefore, determinant of adjoint A is determinant A times A inverse. Remember, determinant A is a number. It's like a K. Let determinant A is equal to K. It is basically determinant of K A inverse. This is K power n times determinant of A inverse. So determinant of adjoint A is K power n. Now A into A inverse is I. So take determinant. Determinant A into determinant A inverse is 1. It's determinant I, which is 1. So determinant A inverse is 1 by determinant A. So this is determinant A whole power n. This is 1 by determinant A. So determinant A whole power n minus 1. I should have given this the result first. I'm sorry, I made a mistake. I thought I have given this result in the theory. I just checked and it's not there. I only gave adjoint of K. I didn't give determinant of adjoint. So determinant of adjoint of a matrix is determinant of the matrix power n minus 1. Okay. So determinant of 2 adjoint A is determinant of, so it's 2 times 2 power 3 times determinant adjoint A. Correct? Because this is just direct determinant of Ka K power n determinant A. Now determinant of adjoint A on the other hand is determinant A whole power n minus 1 whole square. So, but what is determinant of, so 4 is equal to 2 cube into determinant A square. 4 is equal to 8 determinant A square. So determinant A is plus or minus 1 by root 2, which is option D is the correct answer. Okay. Um, yes, I did give that. Determinant of Ka is K power n determinant A. I did give that, Siddhi Vinayak. I did mention that. In fact, I gave an example and said if I multiply everything by 5, the thing will get multiplied by 5 cube. I said that. I just didn't do it specifically for adjoint. That's all. But as you can see, you can derive it like the way I just showed you. Okay. Anyway, so please note that this is a very important result. Determinant of adjoint A is determinant A power n minus 1. Okay. It's a very important result. Okay. In fact, the next question uses this. Please go ahead and do question 4. Please go ahead and do question 4. You can use this idea. Determinant of adjoint A is determinant A power n minus 1, where n is the order of the matrix. Okay. A few questions. Hari Prasad has asked, Is there a more direct and intuitive way to find adjoint? No. If it was, that's what I would have taught you. Okay. Cofactor is cofactor of A times transpose is the most direct. Okay, I won't call it intuitive and easiest. Remember, JE does not expect no need for 4 by 4, 5 by 5, etc. 3 by 3 is all that you will need in JE. 2 by 2 is trivial, 3 by 3 is where the work is. Rakshana, how are adjoint and transpose connected? So, transpose of a matrix and see if A is n by n, adjoint of A is n by n, and adjoint of A is cofactor of A's transpose. Adjoint A and A transpose are not really linked. Okay. Now, what you can say is, remember, I'll come to that later as a property. See, what we know is determinant of A is determinant of A transpose. This you can use. Is determinant of K times adjoint A is K power n minus 2 determinant of adjoint A? No. No, see, determinant of K times any matrix B is K power n determinant B. So, determinant of K times adjoint A is K power n determinant adjoint A. It's not K power n minus 2. But determinant of adjoint A is determinant A the whole power n minus 1. See, whether you write of determinant of adjoint or determinant of A, that matters. This is not correct. Okay. Sarvesha has asked a tough question. Will Sarveshwar, sorry. Adjoint A, the whole inverse be equal to adjoint of A inverse? You should actually check it and see. Okay, these are all. See, let adjoint A is equal to B. Okay. Now, is adjoint of A inverse is equal to B inverse? Then B into adjoint A, sorry, B into adjoint A inverse must equal I. Okay, this is if this is true. That means adjoint A into adjoint A inverse is I. This is adjoint B into adjoint A is adjoint of AB. If all of these is true, okay, and this is if adjoint of I is I, but it's correct because adjoint I is determinant I inverse. It's all 1 into I, so it's I. So you're right. So the answer is yes. Prove it like this. Okay. Okay. For this question, the way we have to do is we have to find the determinant of adjoint A. Okay. So in this case, determinant of adjoint A is 1 into 0 minus k plus 2 into 0 plus 1 plus 4 into 4k plus 1. So it's minus k plus 2 plus 4 plus 16k. Is that correct? In k plus 6. Okay. Now determinant of adjoint A is determinant A whole power n minus 1, which is 6 power 3 minus 1, which is 36. Therefore 15k plus 6 is 36. So 15k is 30, which means k is equal to 2. Option C is the correct answer. Okay, can we write determinant of adjoint A is determinant A whole power n minus 1, where n is order of the matrix? Yes, Sergeant Varghese, yes. You are right. Okay, okay. Now, um, okay, I think this question, we should be able to do question 5. Read the following passage and answer the question. This is not related to adjoint. This is related to inverse, because I had forgotten to put this kind of question earlier. What is the value of AB? This is a slightly tricky question. So think about it and see. Let I plus A be a non-singular matrix and B is I plus A the whole inverse. Okay. What is the value of AB is the question. Okay. Question 5 may be easy. 6 and 7 may be a bit tricky. Okay. Let's take 5 minutes extra so that I can finish one or two of these questions and also do the summary like what Manas had asked. Okay, I'll definitely do a summary of everything related to adjoint. Okay, please stay back for another maximum 5 to 10 minutes. So let's just finish one more question. This one, I think the question 5 is fairly straightforward. Many people have got it right. Okay. I know it will not be possible mostly. Can I still do it? No. Vijay Srivatsan, no. Definitely no. Don't do that. It's wrong. Okay. P, since B is I plus A inverse, okay, B into I plus A is I. That's the whole point, right? If A is B inverse, AB is I. Therefore, B plus BA is I. Therefore, BA is I minus B. But we didn't want BA, we want AB. Okay. We can also write I plus A into B is I. This means B plus AB is also I. And this actually solves. So that means AB is I minus B. This is what is expected for question 5. But because I tried to put B into I plus A as I instead of I plus A into B, both of these are correct. This is correct and this is correct. Well, what I have done is I have also solved question 6. Unfortunately, I didn't give you the choice of solving this. Okay, but it's fairly straightforward. So question 6 is done. The correct answer is null. Okay, so the last thing for you to do is question 7. Okay, see if you can do question 7. Is there something that you can write? BC is CB, BC is null, BC is I, none of these. Please go ahead and do question 7 because 6 I solved already. Just a minute. Okay, let me just check. C is I minus A. Okay, so B, see, B is I plus A, the whole inverse, and we found that AB is, I think, I minus B, correct? AB is I minus B. Now, what is BC? Okay, BC is B into I minus A, which is B minus BA, but we also found BA is I minus B. So B minus, sorry, B minus BA. Just make, let me just clarify. AB is I minus B minus BA, which is B minus, wait, is there a mistake that I've made? This is 2B minus I. CB is uh, I minus A into B, which is B minus AB, which is B minus I minus B, which is also 2B minus I. So the correct okay, correct option seems to be option A. BC is equal to CB. Most people had put option C, which is BC equals I, but it looks like BC is actually 2B minus I. B is not the same as I. Okay, so that's not correct. BC is equal to CB is correct because of the property that we just proved earlier. See, these are kind of tricky things related to inverse, is all I can say. Okay, both answers are option B. Which one? Okay, I think some previous question. Okay, let's stop here. The other part regarding equations part we will do next class. In fact, that and determinants are very strongly linked. So I will do it along with determinants. Okay, so we will have a test on all these ideas next class also. Okay, let me just summarize like what Manas had. Manas is the person, right? Wait, Manav or Manas had asked. Manas, yes, had asked. Okay, Ishita Bhattacharya, A into AB is equal to AB into A in general, or this question? In general, you cannot, it's A, you cannot do this. In this particular case, it may be right. That's a different thing. I'm not sure what your doubt is, Ishita. In this particular question, it works. Maybe that's what I think you mean. Okay, because AB is I minus A. Is it working? I don't know. You check and see. But in general, if you are trying to say any three matrices, can I swap? Obviously, no. Okay. Okay, let's do a summary of everything that we have done in adjoint, okay, cofactor, etc. See, adjoint of A is transpose of cofactor. Cofactor of A is C11, C12 small, where Cij is minus 1 power thing, determinant of submatrix. Okay, and what we find is that A into adjoint A is equal to adjoint A into A is always determinant A times I. It's not determinant A times I. Remember, determinant A is a number like K. If any doubt, if you're confused with too many symbols, adjoint, determinant, inverse, etc., immediately replace determinant A with a K. K is usually associated only with scalar. Okay. So now determinant of um, okay, I just put K as determinant A, but yeah, you can also say determinant of P times A is P power n determinant A, where P is a scalar. Scalar means just a number. N is the order. Okay. Determinant of AB is determinant A, determinant B for A comma B being n by n. Okay. This is a very, very important idea which we haven't proved and we are not going to prove. Okay. Then, okay, Ishita said that the power sequence being constant, then it's equal. Could be, but okay. Sanjana, sorry, I just saw this. Okay, is A plus B into C is equal to AC plus BC, not AC plus AB. Timbaya, AC plus BC. Distributive law holds good. Correct. Question 5, 6, the whole thing I can't explain. Okay. Uh, Sorry, it's going to take too much time now. Okay. Now for the last thing, so we did a lot of properties related to adjoint. Okay. So first, adjoint of AB. See, the first thing is adjoint is related to inverse. Adjoint A is determinant A times A inverse. And A inverse is 1 by determinant A times adjoint A. Remember, for 2 by 2, adjoint A is just some entries swapped and all that. That's why A inverse is 1 by AD minus BC times adjoint. Okay. If A is ABCD, okay, adjoint A is D minus B minus C A. That's why A inverse is 1 by ADBC D minus B minus CA. Okay. Now adjoint of KA is K power n minus 1 adjoint A. Okay. Determinant of adjoint A is determinant A whole power n minus 1. Okay. Determinant of A inverse is 1 by determinant of A. Why? Because A into A inverse is I. Determinant A into determinant A inverse is 1. Okay. You can take determinant on both sides of a matrix equation if it's all square matrices. Okay. So all these properties. Okay. Determinant of 2 times A is 2 power n determinant of A. Or K is, I already wrote that. Okay. So determinant of adjoint. These are all the things that uh, you may have to get very comfortable with. But in fact, this is all the properties related to adjoint that you need to know. Okay, the definition and some of the properties, if you have, it's perfectly enough. You don't need anything more related to adjoint. Adjoint is a very powerful idea, but surprisingly, not too many things. Everything else you can derive. Somebody asked, can I say adjoint of A, the whole inverse is all that you can derive? Okay, with whatever has been given already. Of course, the most important thing that we wrote, not most, adjoint of AB, adjoint B, adjoint A. Remember, none of these properties work for plus. A plus B whole inverse equals A inverse plus B inverse. Wrong. Adjoint of A plus B, you can't write it as adjoint A. See, when you add two matrices, individual entries are added. That will be very, very different from what you get when you do thing on the whole. Shami Sambarwal, how is determinant of adjoint A determinant A whole power n minus 1? Determinant of adjoint A is determinant of determinant A times A inverse. Remember, adjoint of A is a matrix which is determinant A times A inverse. Remember this. So it's determinant, and remember, determinant of determinant is not some illegal operation. Determinant of determinant, this is some K. So this is determinant A power n times determinant of A inverse. So determinant of Ka is K power n determinant A. This thing here, A inverse is the matrix and determinant A is a number. You are multiplying the matrix A inverse with a number. So that number power n determinant A inverse. But determinant A inverse is 1 by determinant A. So this is determinant A power n minus. Obviously, all of these assume that determinant A is not 0. Otherwise, things will go for some toss in all these proofs. Okay. I hope, Shami, the last two steps I put that. Okay. Vijay Srivatsan, I did question 7 in a different way. I took I minus A as I plus A minus 2A and found BC and CB, which turned out to be equal. Perfectly fine. Yes, yes, perfectly. Your thing seems perfectly correct. Okay. Any other doubts that I just missed? Clearly, this is wrong, Vijay Srivatsan. Yeah, I think that's about all the doubts. Okay, do go over the class again. Okay, the extra lesson in the online thing where adjoint is covered, I'll ask the mentors to assign that also. But you can also go over this if you have any doubts. I'll also try and give some extra problems on adjoint and all that later. Okay, you will get more. It's just that I didn't want to do to everything in this class. Okay. Okay, so let's stop here. We are well past the time. Okay, I hope I've cleared all the doubts and this thing. So do give your feedback. Of course, you can bring to next class any doubts you have on adjoint, inverse, etc. Okay, okay, guys. Good night. I'll see you next week. Okay, bye bye.